Of the morning, for our second speaker of the morning session, we're happy to have Antonella Grassi, who's going to tell us about Kodaira's birational classification of singular elliptic fibers for threefolds.
Okay, thank you. Thank you. I'm very honored to speak at this conference to celebrate the many contribution of Professor Shukarov to algebraic geometry and to birational algebraic geometry. His contributions are continuing, and I'm looking forward to his talk on Friday night at 11 o'clock on 11 p.m. on Bologna time, but I'm looking forward to following it. And the name of Professor Shukarov came together when I was learning birational geometry. So at the very beginning, its first thing was the non-vanishing theorem, which is also quoted on the poster for the conference. So again, happy belated birthday, I guess. So
thank you.
So the blank page was about this. And I'm going to talk about genus 1 fibrations. And so the genus 1 fibration will start from Y to B, a genus 1 fibrations. And so the fiber over a general point is a smooth genus 1 curve. And the fiber will be smooth over open and then set in the basis. And I will call them an elliptic fibration when the genus 1 fibration is a section. And I will write it like this, which means the elliptic curve is marked with a point. And we heard in the previous talk, elliptic fibration come with a discriminant, and the discriminant is in the base, the loci where the fiber, the inverse image of the fiber is not a smooth elliptic curve. So, and this discriminant is stratified, and I will mostly considering threefold. So the stratification will go in sigma, sigma 1, and sigma 2, and we'll stop there. And from arithmetic, the sections, if there are sections, they form a group, and this is called the Mordeville group, is the Mordeville group of the fibration from Y to B. And I will be talking over the complex numbers, and in addition, mostly the varieties will be projective varieties I'm talking about. So Kodaira classified over the complex numbers this study over the complex number, the relatively minimal genus 1 fibrations with where on surfaces, so X can, without loss of generality, be assumed to be smooth. And he proved various facts. One is the canonical divisors formula, which says the canonical divisor is the pullback of a canonical divisor of the base and another divisor, and Q divisor over this divisor here. And this is supported on the ramification on the discriminant, where the fiber are singular, and in modern language, we would say that the base is KLT singularities. And then Kodaira gave an explicit description of all the singular fiber of discriminant. And this is the description. So there is a finite, almost a finite list, a finite family, and on three infinite families, and one correspond to the multiple fiber. And one can associate to them dual graphs, and these dual graphs are the extended graphs of the algebras with the same name. There is also a corollary which follows from Kodaira's work, which is that the type of the elliptic fibration, the genus, the canonical divisor formula determines B and much of B and much of the birational invariance. For example, if we have a K3 surface and an elliptic fibration, the fiber would be a P1. The rational elliptic surfaces we saw in the previous talk also map elliptically onto P1. So one could ask the question, what happens if the dimension is greater or equal than 3? And for all these facts, one must have a suitable interpretation and statements as canonical divisor formula, this singular fiber, and in dimension 3 and higher, there is another question, which is the question of equidimensionality, which is vacuous in dimension 2, and we must have another statement. And what I'm going to talk about in this talk are about some of the questions, some of the answers, and some conjectures which come out of this context, and some applications. Now, I want to say just a few things about quickly why these 3 points are not trivial in dimension 3 of higher. One is that even with X and B smooth over a base, there are examples where doesn't exist over the same base birational equivalent elliptic fibration where the formula of a canonical, this formula holds. And even this, if we relax the hypothesis that X prime has KLT singularities. And then there are also examples where the fiber is not, where the fibration is not equidimensional. These are both rather easy to construct. And then another one, if you want, easy observation is that when we have in dimension 3 and the singular locus, we go deep, so into the codimension 2, in the two-dimensional strata. So the thing of the discriminant, so the singular locus of the discriminant, then the fiber will depend on the singularity at the point, the singularity nearby on the discriminant, and also on the choice of X, the relative minimal model. So will up to flops. The description of the fiber will depend up to flops. Some example to keep in mind, which will come up later in the talk, starting from surfaces, is the pencil of two general cubics in P2 blown up gives an elliptic fibration, and this elliptic fibration as section, and generally we can have the rank of the veil of Y to P1 is equal to A, the rank of sections. And the discriminant is just given by 12 point. Variation on the theme without a section, one can take a sextic with 9 nodes, and then a smooth elliptic curve passes through the 9 nodes, and we take it double, and this gives what they're called Alfvén's pencil and the rational elliptic surfaces again, but this case here there is no section, but there is a 2 section. And again here the discriminant is given by 12 nodal curves and a multiple fiber. Last case and test case, which is the case of a Weierstrass equation. So locally, this is the equation of exactly of the elliptic curve in the plane, but the coefficients are functions on the basis, so line bundle, a section of line bundles of the base to be precise. And there is a theorem of Nakayama which says that if X and B are manifolds, complex, and any elliptic fibration with a section as a birational morphism, really birational morphism to W, which is of this form. It's a Weierstrass model. So birational to something which has a local equation of this type. Now, relevance of genus 1 fibration down here in a conference of birational geometry, we all know Kodaira dimension L-1 and dimension N, they have an elliptic fibration. This imbues the elliptic fibration as test case for example, the work of Fujimori. And there are also test cases for outside, slightly outside birational geometry, one fibration of Lagrangian, of algebraic geometry, and even other fibration. So G2 spaces or special holonomies, and lots of examples which are relevant, which are built onto model onto what happens to elliptic fibration. They are studied for their arithmetic properties, and they also appear in the study of high energy physics application, especially in the context of what's called the F theory. And in this case, X is a Calabi-Yau, where a lot of work has been done to show that these elliptic vibrations are actually ubiquitous. There are studies, even these days, with artificial intelligence. They show that most of them, most of Calabi-Yau, have the structure of genus 1 or elliptic vibration. And I use the word Calabi-Yau, so I'm going to say what I mean by Calabi-Yau, which is variety with trivial canonical divisor. And for now, I'll take it with q factorial terminal singularities. This number equals 0, and for the dimension between 0 and x, between 0 and the dimension of x. So the standard definition of Calabi-Yau. Some of the things that I'll say are also okay with canonical log terminal singularities, and perhaps without q factorial, the definition of q factoriality. But I'll stick to this definition to start with. One example, and an example which is a series of examples, which goes by the name of the Schoens, because were first constructed by Chad Schoen, again to answer a question of the physicist of the topological types of Calabi-Yau, which has been recently answered by several of the people here and some of the organizers. And so some of the models are, we're taking a rational elliptic surfaces, the one that I talked about at the beginning, like P2 blown up a 9-point in general position or not. And I'm taking the product over P1, and then, if necessary, resolve it. And I find them interesting because these models, so now there is an elliptic vibration between X and Y, one of them, and the resolution and Y. And they're interesting because they're relatively simple to construct, but they display many properties of general Calabi-Yaus. One is the singularities can be q factorial or non-q factorial. This can be a q factorialization or not, and they can be smooth or not smooth. And the Mordell is also interesting. And the Mordell is interesting, but is also manageable because we know that the Mordell of a rational general rational elliptic surface is between 0 and 8. So this is one of the examples which will occur also later. Now, going back to the question of Kodaira for a higher dimension, this is something that I started doing in my thesis when I had first run into Professor Shokurov's results. And I did it for threefolds. And then many things happen in the minimal model program and birational geometry. So I'm just collecting here some of the results. So and I'm putting dimension x less or equal than fine, also because this is the bound where many of the theorems are known in minimal model that we'll use below, and also is the number. 5 is a magic number, which is relevant for application to the physics of string theory. So one is there is a given x to b, genus 1 fibration. Then there is a birational equivalent fibration x to b prime, where many of the which generalizes what Kodaira did for dimension 2 and for surfaces. One is this one, the canonical bundle formula, and then the singularity are appropriate. So one is minimal in some sense. This is minimal in some sense, and in a good sense. And if a dimension is equal 3, x Calabi-Yau, more general and without multiple fiber, then the base is smooth. And the loci, where the fibration is not equidimensional, this is on as codimension greater or equal than 3. So in particular, if we have a genus 1 fibration of a threefold, then is equidimensional, because we don't have the codimension 3. And then something more, if we don't have multiple fibers, then the surface, the base surface, in the case of threefold, there are now multiple fiber, the base surface can be taken, we know, smooth, and one of these surfaces. And Mark Gross also said that in the case of, this is actually more general in Calabi-Yau, then in the case of Calabi-Yau, when is even with multiple fibers, it can still be classified, and there are a final certain, there is a handle on what they are. Now, on this builds up all the boundedness and a lot more of birational geometry, and I put it a lot of star because there are a lot of authors, and some of them are here with all wonderful results. So this is star does not refer to a formula, but it's like an appreciation, many stars. So I should add more stars to boundedness results on family results on families of Calabi-Yau. And I want to talk something here. I want to mention something also, which also builds again on the classification, on the basis, and with existence of section and the Morricone and somewhat birational algebraic geometry in a physics proof. And the physics proofs is the following. Then if a fibration, relatively minimal fibration of a Calabi-Yau has a section, so relatively minimal, then if it's a K3, then the rank of the Morday veil is less or equal to 18. And then if it's not P2, then the rank of the Morday veil is less than 16. And if it's P2, then the rank of the Morday veil is less or equal than 24. So this is approved by Lee and Weigand. This is in a physics paper. There is birational geometry in it, the description of the basis, and physics. And this physics is the physics which is in the proof is not translated, doesn't have a dictionary for a math proof. So I pass it partly as a conjecture, because for the case of the K3, this was proved by Cox. The rank of the Morday veil is actually less or equal than 18. And Cox, Klosterman, and Kawata actually gave a construction then every Morday veil is actually reached for the case of the K3. Now, so for K3 match, for Calabi-Yau threefold, Then there are constructions up to the rank Mordevale equal to 10. And up to 9, there are many, they're plentiful, it's easy to find them, and they're interesting. But then for 10, there is only one that we know of, and one that we computed looking at a Schoen, one of these Schoen, which is comes with a Schoen with non-Q factorial singularities. And so this is computed, and there is a family also conjectural due to Elkis. So conjectural in the sense that the fibration has rank on Mordevale 10, but is conjecturally a Calabi-Yau. Because it's essentially an arithmetic construction. It's not a birational geometry construction. And so again, our construction is a resolution of the Schoen model and has interesting deformation property, is not an accident, and was discovered by Namikawa and then followed by Rossi, the threefold itself. And then we did the Mordevale. And now going back to Kodaira. So what we have now with birational geometry, we have many, we have generalized what Kodaira did over the complex numbers in many of these points, except perhaps the interpretation of the statements of the classification of the fibers. And this is what I'm going to talk about today. So I'm going to talk about two. So an interpretation and statements. What do we mean? What can we say about Kodaira classification, at least for threefold, or hopefully in codimension or for discriminant on the two strata of the discriminant. So I'm stopping for a second and ask if there are questions before I go forward. Okay, so I'm going towards the second part, and this is a conjecture that I made with my collaborator, Timo Weigand, which is we call stringy Kodaira, which is that it exists a Kodaira type classification of singular fiber in codimension 1 and 2 of the base up to birational equivalence, and that the classification, this is a birational invariant. So if you think about it, also Kodaira's classification for surfaces is birational invariant because it's a classification is up to birational equivalence because it's a classification on relatively minimal surfaces. Now, what's a statement? So what I'm going to do, I'll try to work towards making a statement and talk about what we mean by birationality. And for the birationality, we can prove it when X is a Calabi-Yau threefold, and under general condition, a Calabi-Yau threefold with Q factorial terminal singularity in a sense, which I will explain in what's coming. And this is verified by large classes of examples in the physics literature, and for X, smooth Calabi-Yau. Now, the work which led to what I'll call this assignment. So the assignments, it means birational classification of the singular fiber comes from the analysis of the spectrum in physics, a spectrum associated to Calabi-Yau. So the string literature says that F theory on XP so X be a genus 1 fibration on a Calabi-Yau is dual to a 2B on B with branes. There are duals also on heterotic duals, and there are also mirror duals. The claim is that the geometry of fibration is tightly related what's called to the massless particle spectrum of the physics. And quantities in the spectrums must satisfy relations. And these are called the anomaly cancellation for the theory to be consistent, because it's a quantum theory and it's a gauge theory. So the question is, first question is, build a dictionary between the elliptic fibration and the physics. Then what we produce a geometric formula of the anomaly cancellation, and then they calculate so the quantity exactly in the spectrum, and then the birationality, the birational invariance will come as a geometric property inspired by the anomaly, by the geometric anomaly. So I'm going to talk about this one. So the dictionary, there will be a correspondence. I'll focus on this anomaly cancellation and this geometric counterpart. And I want to mention, but as a pure conjecture, there is also another anomaly, which we'll see at the end, which is stated clearly in geometric terms. But as far as I know, there is no plan. There's no approach how to prove this in algorithmically, or to give a proof, there is no insight how to prove it in the realms of mathematics. So the geometric property will give us what's what I like to call stringy Kodaira. So start the spectrum. So in string theory in the 90s, from the 90s on, there is the statement is that the geometry of smooth Calabi-Yau variety, elliptically fiber, so they're assumed with a section, and the discriminant, so to them is they're associated Lie algebra or A, B, C, D, F, G type, and U1s and certain representation. So U1 is really the U1. And in the string literature, the assignment of the algebra and the representation are given by assigned ad hoc, so case by case and through duality. And then the physics approach is to verify the consistency of the assignment to see that the theory doesn't change, that the theory is consistent through the anomaly, and then to verify ad hoc, so in case by case, one by one, then by flops, under flops of the Calabi-Yau, the assignments do not change. So the theory, although the fiber, the Kodaira type fiber changes, then the assignments associated to the spectrum does not change. And in physics, the consistency means these anomaly formulas. And the anomaly works when they exist when the dimension of the Calabi-Yau is equal to 3. So they don't exist for K3s, and they don't exist in dimension 4. Now, a program that I've been working on for a long time is with a various set of collaborators, is trying to determine in mathematics a way to associate it to this elliptic of genus 1 fibrations, algebra, and then their representations. And then to define geometrically a correspondent, a geometric gravitational anomaly equation, and then to prove it, give a mathematical proof for this consistent relationship for Calabi-Yau threefolds, and prove properties that follows, among which birational invariance. So now the assignment here does not depend on the Calabi-Yau condition. Neither in physics nor in the mathematical assignments that we come up with do not depend on the Calabi-Yau condition. However, the Calabi-Yau condition works as a local to global principle, sort of to glue together all these local assignments. And only for Calabi-Yau threefold, we're able to make a consistency statement, which is an equation, which we call the geometric anomaly equation, and to show birationality. So we can show it from Calabi-Yau threefold. So we hope that for threefold with with Neff threefold, it's possible. We hope that it's possible to extend the statement also for threefold with Neff canonical divisor. Now, what are these assignments? So I'll start with the case. I want to talk about the assignments. So I'll start in the case when the base is smooth, and then I'm going to talk later about when we have singularities. So when X is smooth, and the hypotheses are in the one from the minimal model program. So we have X relatively minimal. The canonical divisor of X is the pullback of the canonical divisor in B, and this is equidimensional. We can do it, we can assume it without generality if there are no multiple fibers, and otherwise we put in the hypothesis and B is smooth. So the discriminant is stratified, has a locus of which is a curve in B, which is a surface, and then there are points, and these points are typically singular points of the discriminant. And so the assignment, which will build the counterpart of the Kodaira classification, are the following. This actually doesn't exist in Kodaira, but it's relevant for higher dimension. So if a fibration has a Mordell with rank non-trivial, then we associate it, which is called an abelian gauge algebra, and this is U1 to the R. And surprisingly enough, this also an impact on the type of fiber, the Mordell group, which we don't see on surfaces, because this happens in codimension too. And then we associated a non-abelian gauge algebra, actually a direct sum of Lie algebra, and these are associated to the curve, so to the codimension, to the general point of the discriminant, and this assignments to a generic component, reduced component of the discriminant. We can associate an algebra in different ways. One, if there is a section going through Nakayama's theorem and the Weierstrass model by the generalized state algorithm, we can assign an algebra, or we can do it by what we call the refined Witten's method. So by computing intersections, so constructing a lattice intersection, and then realizing that the relevant intersection gives an algebra, the Cartan algebra of a Lie algebra. And that will be the Lie algebra associated. And then there is a third method, which uses vanishing cycles, so which is a cross between algebraic geometry and topology, and uses vanishing cycles, Picard-Lefschetz monodromies, and weights, so and deformations. And one can associate it again by this way, also Lie algebra. So let's go back to the case of surfaces and see what this means. So this one here, if we have a section, then we're going to construct the Weierstrass model, and the Lie algebra then we associated is the Lie algebra of the ADE diagram that we got in the Weierstrass model. They have an intersection. We learned that the intersection is also correspond to the intersection of the algebra. And then for vanishing cycles, this means that when we deform it, we can deform it locally, and the deformation, say for K3, locally for K3 is hyperkähler, or actually in general doesn't have to do anything fancy. So the deformation is diffeomorphic to the resolution. So for K3, this is for surfaces, and for without multiple fiber. And in general, but for threefold, one has to use a more careful attention. And so the theorem is that actually all these three methods give the same Lie algebra. So the assignment is actually well defined. For the S1, so the top strata of the discriminant, the reduced curves. There is another method which I just learning about it, which is a method which uses mirror symmetry and Gromov-Witten Gopakamura-Vafa invariant to associate the algebra, but it's not direct on the Calabi-Yau, but uses its mirror and computations. So now I want to talk about the state representation, always associated to the one strata, not just to the algebra. And so again, one can use to the one strata if the algebra is not simply laced, then one needs to associate it another algebra, another representation, and this is determined by the branching rules, and this is associated also to the codimension 2 strata, where the fibration, the codimension 2 strata of the discriminant, which no simply laced algebra have. This representation, the assignments about strata, the S2 strata, sigma 2 strata of the discriminant, so the singular locus of the discriminant, in physics they are called the charge matter hypermultiplets, and they're part of the spectrum. So we're going now deep in the discriminant, and again we refine the various methods, and to points, singular points in the discriminant, we associate a representation which we call rho of Q as a tensor representation in all the Lie algebras, which comes associated to the branches of the discriminants to the points Q. And this can be obtained algorithmically in three different ways. One, so we call the refined Katz-Vafa algorithm when there is a section. And this builds on Turino simultaneous resolution of rational double points and the work of Priskern, Grothendieck, and Slodowicz about the slides, of which gives the Lie algebras and singularities. Another one is again with the intersection. And then the third method is again with vanishing cycle, and is not complete because we cannot do it for some cases. So it's 3 minus a case. And the conjecture in this case is that all these three methods give to the codimension 2 strata the same representations. This is a conjecture because it has been verified, and the three methods give the same representation, the same assignments in many examples, but this is a conjecture in general. We don't have a mathematical proofs like we had in the previous cases that these are equivalent. And there is one more case. Two more cases actually. When we have now I'm going on a Calabi-Yau, so we're going in the realm of Calabi-Yau threefold or Gorenstein. So when the singularities are hypersurfaces to the point on the base, if the Calabi-Yau has a singularity, then we need to associate to it the Milnor number of the singular point over the codimension 2 locus and the discriminant. And one more case, which is the one related to the U1. So we are in the codimension 2 loci of the discriminant. And typically this occurs in correspondence of a resolution of a non-Q factorial singularities. When we do have a section, so we have a Weierstrass model, then this point is actually determined by a relation of the section. This can be made explicitly. And the number here, which associated to the codimension 2 loci, is related to the genus 0, is the genus 0 Gopa-Kumar invariant of the fibers. And this is again work in progress, because even the physics here is no guidance to us. And it was expected generally that this number here were equal to 1, but it's not so the case. And we saw it in the example that I was saying, I was mentioning before, the example of Namikawa-Rossi, where the rank of the Mordeville equal 10. The discriminant is actually rather simple, and it's a bunch of cuspidal curves, the discriminant. And on sigma 2, the singular locus of the discriminant over this is in the base, the fiber looks like a Kodaira type 4, but this is not picked up by any non-abelian representation, because there is no non-abelian representation. However, the U1, this section actually pick up the Gopa-Kumar-Vafa invariance, and they determine that there is a singular fiber here, which it looks like of type 4, or Kodaira type 4. And then we are coming up with other general cases where this Q1 is actually strictly positive. It's here. And they don't need to be separate. So from the previous Q before, but in this case it is. So I want to show a table, which is a contained table that we have. We constructed originally part of it with the Morrison under general hypothesis. So we computed these assignments. So Calabi-Yau threefold, this is the general on the type of Kodaira type over the codimension 1 strata of the discriminant, so the top strata of the discriminant. This is the algebra that we constructed following the assignments. And these are the various representation. And these are the Milnor number of a singular fiber. So it means that the Kodaira type, which is in general, can be extended also. These are the loci of codimension 2 strata, this in the codimension 2 strata. So the plan is to substitute to the Kodaira classification a Lie algebra, a string of numbers, so a Lie algebra and its representation. And the Lie algebra and its representation, each of them, they substitute the Kodaira, a stringy Kodaira. A Kodaira also classification also in codimension 2. So instead of getting the description, the explicit description of the fibers, we could get a Lie algebra, and in codimension 2, the representation with the Milnor number and this Gopa-Kumar-Vafa invariant. So again, this is the assignment on the codimension top strata of the discriminant, and this on the deep down on the singular locus of the discriminant. So this is the assignment, and is the assignment without multiple fibers. So, but the claim is that this can also be assigned when generalized, when the base is singular and there are multiple fibers. But it's a little bit more involved to write. So what we use what we use in the proof: non-degenerate pairing, morphification, versal deformation, Milnor number, enumerative geometry, representation theory, and birational geometry, especially Q factorial versus non-Q factorial singularities. Now, the question is that some of the proof works also for some more general singularity, for example, for KLT. But we don't know exactly the assignments. So in physics, the assignments are what they're called, I said, the charge hypermultiplets, and they're denoted by HC. So the physics result is the following, is that if we have an elliptic fibration, XP smooth, Calabi-Yau, equidimensional with section, then the gravitational anomaly are canceling if this magic number is satisfied, and the magic number has where these are the ingredient of the magic numbers. So these we know, and we know well. The H charged are the hypercharge hypermultiplets, which I defined in the assignments. They come from the assignments. And now the claim is that we did with Day Morrison a long time ago. Again, when it's smooth, we can translate the gravitational anomaly equation in terms which are more familiar in the terms of algebraic geometry, except again for this quantity, which is H charge, which comes from the assignments. Now, for genus 1 fibration, then we defined with Weigand this number, which we called R. And then we say that this number R satisfied the geometry anomaly, if a fibration satisfies the geometry anomaly equation, when R, which can be computed here, is equal to a right-hand side, which is a formula which involves all the representation, all the assignments that we mentioned before. And this corresponds to the codimension 1 strata of the discriminant, this to the codimension 2, this to the codimension 2, and this to codimension 2. And there is even a part which corresponds to the multiple fiber. If there are multiple fibers and the base is not singular. Now, the theorem is if we have a general elliptic fibration, then an X is a Calabi-Yau, Q factorial terminal singularity, then the geometric anomaly equation holds. So this assignment, which represents the Kodaira type fiber in general sense, the stringy Kodaira, pack in the Calabi-Yau to satisfy the left-hand side this equation. K top, which we know, and something else which we know from the basis. And this is also verified in many examples. And the point here, I guess I have 1 more minute. So the Calabi-Yau condition works as a local to global principle, which takes the local assignments to global assignments. And as a corollary, we have that for general Calabi-Yau, then the representations are also birational invariants. So I want to conclude just with a slide of questions, which I can leave it there in the last minutes. So what happened when we have KLT singularities and dimension 3? and when the fibration is not a Calabi-Yau. And actually what happened in general, because much of the construction that we built, not much, some part of the construction that we built does not at all uses the fact that we have a genus 1 fibration. So how can be extended? And another question, something which probably not related to a generalization of Kodaira, to understand in mathematical terms what are the implications of this abelian anomaly equation, which it's a cross between arithmetics and birational geometry. Okay, so I'm stopping here, and thank you very much.
Thank you very much, Antonella, for a very nice talk. Are there any questions?
So I have a very big question. Is that so? How much will the boundness of elliptic Calabi-Yau threefold, I mean the recent work of already help with the classification?
So we did not. So that's so we did not use it now, but this is like something that I like to talk to them about it. Actually, how can we build on them to go one step further? Something.
Okay. Yeah.
To basically see how many, so sort of kind of like a vague idea, but how many actually Lie algebra we can pack in.
I see. All right.
Yeah.
Thanks.
That's another question. Yeah, exactly. Yeah.
Actually, I have maybe two questions. One is it's more maybe like a remark. Exists alternative version of classification of Kodaira, but with singularities in terms of complement. Then we have these exactly exceptional cases, but when we have one-dimensional base. But of course, when we consider two-dimensional base, here arises one additional problem to discriminant, that locally near point we have also, in addition to so-called divisorial part of adjunction, we have also modular part of adjunction.
Exactly. Yeah.
Why you do not take into account this modular part of adjunction? Because it locally may be not removable from point, even for non-singular base.
No, we do take it in account.
You take, because I
I just didn't talk about it. Yeah. So there is actually a good part of literature related to the modular and non-modular part, which in physics language is called like the non-Higgsable cluster. So yeah, we do. It's definitely up to the point. Yeah, definitely. Yeah.
And it seems to me if we have threefold and we have this theory of complements, then exceptional case, it's easy maybe to see, not very easy to see, but non-exceptional cases is easy to see. Because in exceptional case, it corresponds to exceptional case for surfaces and if rational surfaces. And in this case, we do not have classification. We know 100 examples. So it's quite difficult problem usually. But it looks you have some uniform algebras.
Yeah. I like to ask that. Yeah, I like to talk to you about it. Yeah.
Yes, if you would like to talk, I will explain it. It is in some singular version, not for vibration, was investigated by Kudryavtsev, student of Iskovskих. And for classification of singularities, he wrote 100, maybe 200 different types. So in dimension 1, of course, it's much easier, but in dimension 2, even for threefold, it's much more complicated story. Yeah. But maybe through terms of algebras, we have more compact classification. I mean, some 100 types maybe can be represented by one the algebras. I don't know. Okay.
Yeah, thank you. Yeah, thank you. Yeah.
Any further questions? Oh, go ahead. I guess no further questions. In that case, thank you very much, Antonella. And I would like to remind everybody that there is a second part of this online session this evening at 8 o'clock, and I hope to see you there. Thank you very much, Antonella.
Thank you.